Section 4.5, the chain rule. Your homework is problems 217, 218, 221, 223, 233, and 235. So to begin, in single variable calculus, we found that one of the most useful differentiating rules is the chain rule, which allows us to find the derivative of the composition of two functions. The same thing is true for multivariable calculus, but this time we have to deal with more than one form of the chain rule. So we begin with chain rule for one of two independent variables. So theorem 4.8 reads, suppose that x equals g of t and y equals h of t are differentiable functions of t and z equals f of x, y is a differentiable function x and y. And then z of f of x of t and y of t is a differentiable function of t, and dz dt is equal to dz dx dx dt plus dz dy plus dy dt, where the ordinary derivatives are valued at t and the partial derivatives are valued at x comma y. Alrighty, so let's go ahead and do example 1. Calculate dz dt for each of the following functions. And we're given z is equal to f of x comma y is equal to 4x squared plus 3y squared. We're also told that x is equal to sine of t and y equals cosine of t. Okay, so we can do it one or two ways. So one way to do it is to use your definition. And two is to plug in x and y in z, then find the derivative, then differentiate. Hopefully I spelled that right. Okay, so let's go ahead and do that first method. Let's use our derivative definition. So we have this here, we're asked for the same thing, our function z in terms of t. So we have dz dt. By definition, dz dt is defined as dz over dx dx dt plus dz dy times dy dx, or dy dt. And it's important to remember what it means. So the first part is telling you what function, bottom in terms of what variable, right? So we're going to start off by finding our function z in terms of x. So our function z in terms of x, that is here in terms of x, we have just 8x for the derivative. So we have 8x times our function x in terms of t. So that's x equals sine of t. The derivative of sine is cosine. Okay, that's our first part, plus our function z in terms of y. So we look at our function z and take a derivative in terms of y. Remember, this makes x a constant, so our derivative is 6y. Now our function y in terms of t. Our function y is y equals cosine of t. Derivative of cosine is negative sine. So our derivative is 8x cosine of t plus 6y, we should say minus since we have that negative, minus 6y sine of t. Now the problem is that we want our derivative in terms of t, but we have x's and y's. So we have to go ahead and replace those y's with t arguments. How can we do that? Well, we have x's and y's equal to a function in t. So let's make those replacements. So for our final part, we have x and 8, and instead of x, I'm going to write sine of t, cosine of t, minus 6. Instead of y, I'll write cosine of t and sine of t. Okay, so if we clean this up, we have 8 sine of t cosine of t minus 6 cosine of t. sine of t. And even though they're in different order, they're being multiplied, so they're technically like terms. I can subtract them. 8 minus 6 is 2, so I have 2 sine of t cosine of t. Not so bad, right? This is our first way by using our derivative definition of chain rule. Second way to think about it is to plug in your x and your y initially and then take the derivative, which will involve chain rule. But you're using chain rule more of a single variable sense. So if you use our second method, let's go ahead and plug them in. So I have 4 times, and instead of x, we're going to replace x with sine of t squared plus 3, and instead of y, we'll write cosine t squared. Then you can go ahead and take the derivative as normal, since you already have your argument in terms of t, which is what you want. You want dz dt. So we use chain rule. 8, 2 times 4 is 8. Sine of t, the derivative of sine is cosine. So I'll mention this later. And then next I have 6 cosine of t. Derivative of cosine is negative sine of t. So that we have 8 sine of t cosine t. We can bring that negative forward. I have 6 cosine t sine of t. So we're left with 8 minus 6. We get 2 sine t cosine t. So same idea. How do you want to work with it? When you have one variable, in this case we have t that we're working with, plug it in, do your old school chain rule. That's probably the best way to go. But we're in a multivariable now, so we're going to have some future examples where we have to find the derivative of more than one variable. When it comes to that definition, using the definition would be easier. Now, chain rule. In case you don't remember chain rule from single variable calculus, there's kind of this long definition to develop chain rule and kind of develop something that's like U substitution. The way I remember it and the way that I always think about it is the derivative of the outside times the derivative of the inside. That's kind of my go-to thought process in working with a general chain rule. Okay, so there you have your two ways to do this problem A. Now, as we continue, you have the liberty to do whatever you wish to do. But if you use your definition, you'll never be incorrect, right? Let's go ahead and do this second example. Now we see that we're working with one variable only. We're working with t. We have t's here and t here. We're working with t's and we're being asked to find the derivative of dz dt. So let's go ahead and substitute in and then find the derivative of your function t. So what we're going to do is we're going to take our x and we're going to plug it in for x. And then we're going to take our y and we're going to plug it in for y and then take the derivative. Let's go ahead and do that. So if we do so, we're left with the square root of e raised to the 2t power squared minus y, which is e to the negative t power squared. Now don't forget your exponent rules. An exponent raised to an exponent, we multiply. So this gives us the square root of e to the 4t minus e to negative 2t. Now, for the sake of working with derivatives, let's go ahead and write that square root as a rational exponent, so to the 1/2 power. That way it's easy to keep track as we work with the chain rule. So chain rule, take the derivative of the outside, which is at exponent of 1/2, rewrite your problem, and then multiply it by the exponent on the outside. The derivative of the inside. So that we have 1/2. 1/2 minus 1 is negative 1/2. And on the inside, everything stays the same. Now let's go ahead and take the derivative of the inside. That's our chain rule definition. So we get 4e to the 4t plus 2e to negative 2t. Okay, so there we have it. That's our derivative. We just have to clean it up a bit. We don't like to have negative exponents, so let's go ahead and write this as a negative, as a denominator. So we can also factor out a 2 from here. So we're left with 2e to the 4t plus e to the negative 2t. And so this makes 1. So we're left with e to the 4t minus e to negative 2t with a radical. In the numerator, I have 2e to the 4t plus e to negative 2t. And that is our answer. That is our dz dt. Theorem 4.9, chain rule for two independent variables. Suppose x equals g of uy and y equals h of u comma v are differentiable functions u and v, and z is equal to f of x comma y is differentiable function and of x and y. Then z is equal to f of g of uv and h of uv is a differentiable function of u and v, and thus dz du is equal to dz dx times dx du plus dz dy times dx du. Also, dz dv is equal to dz dx times dx dv plus dz dy times dy dv. Now, this is our definition for when we have two independent variables. That first one was for one independent variable. We only had that t to worry about. Now here's a tree diagram to help you remember your chain rules as you're working with them. All right, so let's go ahead and calculate dz du and dz dv for the following functions. We have z is equal to 3x squared plus 2xy plus y squared, and x equals 3u plus 2v, and y is equal to 4u minus b. Okay, so we have all these functions, and notice that we're not in a single variable anymore. We have two variables. All right, so let's go ahead and take the derivative. The best idea moving forward is to use your derivative rules. If you try to use that original plug it in, then take the derivative, you'll end up with a lot of product rule and chain rule combined. So it might be worth your efforts to use your definition. So I'll go ahead and be the good example and use your definition. So dz du is defined by dz du is equal to, and we have this here, right? So let's write that down. Dz dx times dx du plus dz dy times dy du. Okay, let's go ahead and remember. Your numerator tells you what equation you're looking for, your denominator tells you in terms of what variable. So to begin with, we're going to take a look at our function z and take our derivative in terms of x. Now we also have y's. Remember, your y's are just constants. So we have 6x minus 2y dx du. We look at the u, which gives us that 3, plus dz dy. We look at our function z in terms of y. Remember, your x's are constants. So you're left with negative 2x, so my derivative of y is 1, plus 2y, and your derivative of y in terms of u, here's y, in terms of u, we just get 4. Okay, so let me erase those notes above. Let's go ahead and clean it up. So we get, let's multiply in that constant. We have 18x minus 6y, let's multiply in that constant, minus 8x plus 8y. Okay, now do we have our answer? Well, what do we want? We want dz du. We want our derivative in terms of u. So we have to go ahead and last step is to plug in those x's and y's. Well, actually, we can clean it up a bit so it's less substitution. (18 minus 8x gives us 10x. Negative 6 plus 8, we get plus 2y. Okay, now I can go ahead and plug in those x's and those y's with what we have given for x and what we have given for y. So that we have 10, and for x we have 3u plus 2v plus 2 times y, we have 4u minus v. Which gives us 30u plus 20v plus 8u minus 2v. We get 38u plus 18v. And we have found our derivative, dz du. Not so bad, right? So I'll leave it up to you to find your second one, dz dv. You can do it. It's not so bad. And if you get stuck, this is a direct example from your textbook. Check it out. Now we have our generalized chain rule. So for any general sense of chain rule, theorem 4.10 says, let W equals f of x comma y, f of x, x1 comma x2 all the way to xm, be differentiable function of m independent variables for each I in 1 through m. Let xi be xi of t1, t2 all the way to tn. Be differentiable function n of n independent variables. Then dw dtj is equal to dw over d of x1 times c of x1 times c of tj all the way to dw over dxm times dxm over dtj, which is saying that you can take a derivative using chain rule for as many variables as you're allowed. And that's how you can come up with your chain rule. Implicit differentiation. Do you remember implicit differentiation? Recall that implicit differentiation provides a method for finding dy dx when y defined implicitly as a function of x. The method involves differentiating both sides of the equation, defining a function with respect to x, and solving dy dx. Partial derivatives are an alternative to this method. All right, so let's do a refresher example of when you did implicit differentiation. Okay, so the main idea of implicit differentiation is finding the derivative and you have your equation in both the terms of x and y. A common example was, okay, you have a circle equation. How do you find your derivative? Well, that's how you introduce implicit differentiation, right? Now let's do an example. Find the derivative. We see our function is both in terms of x and y. For when we take the derivative of y, we either write a y prime or a dy dx. It just is a notation preference. Okay, so the derivative of x is 2x. The derivative of 3y, 3 times 2 is 6y. We multiply it by a y prime or dy dx. The derivative of 4y is 4, but because we had that y, we'll write that y prime equals 0. Next step, you want to isolate your y prime. So you move your 2x over. So you have y times y prime plus 4y prime is equal to negative 2x. The goal is to factor out those dy dx's or your y primes. So you're left that your implicit differentiation is 6 negative 2x divided by 6y plus 4. So that was implicit differentiation. Theorem 4.11 says implicit differentiation of a function of two or more variables. Suppose the function z equals f of xy defines y implicitly as a function of y equals g of x via the equation f of xy equals 0. Then dy dx is equal to negative df dx over df dy. If the equation of f of x, y, z equals 0 defines y implicitly as a differentiable function of x and y, then dz dx is equal to negative df dx divided by df dz, and df dy equals negative df dy divided by df dz. All right, let's do these examples, or this example. Example 3. Calculate dy dx if y is defined implicitly as a function of x via the equation 3x squared minus 2xy plus y squared plus 4x minus 6y minus 11 equals 0. What is the equation of the tangent line of the graph of this curve at the point 2, 1? Okay, well, let's go ahead and use our definition. We want dy dx and dy dx is defined by negative df dx divided by df dy. So let's go ahead and find the derivative of function f in terms of x. So df dy or df dx. And then also find your derivative of your function f in terms of y. Okay, so here we have our function f. Let's take derivative in terms of x. So only if we treat our x's as variables and y's as constants, we're left with 6x minus 2y plus 4. And df dy is negative 2x plus 2y minus 6. Okay, let's go ahead and use it and plug it into our formula. So that we have 6x minus 2y plus 4 divided by negative 2x plus 2y minus 6. Okay, we have that negative to account for, so you can treat that or work with that however you like. I'll distribute into the negative, into the denominator. So I have 6x minus 2y plus 4 gives us 2x minus 2y plus 6. And we see we can factor a 2 from the numerator and denominator. And that gets you to 3x minus y plus 2 and x minus y plus 3. All right, so that's our derivative. Now our equation is asking for the tangent line. So to find the tangent line, you plug in the point, gives you the slope, and you use your point slope formula. Okay, let's go ahead and do that. Find slope of your point given, which is 2, 1. So let's plug that in into our derivative. So that we have dy dx x comma y of 2, 1. That gives us 3 times 2 minus 1 plus 2 divided by 2 minus 1 plus 3, which gives us 7 over 4. So our slope is 7 over 4. Now we use our point slope formula. We have y minus 1 is equal to 7 over 4 with x minus 2. So our answer is 7 over 4x minus 5 over 2. Not so bad, right? Okay, this was Chain Rule, section 4.5. Hope you enjoyed it. Thanks.